Space is totally fascinating. When I was a kid, my interest in space began basically by reading a book. It was called "We Have Lived in 5 Seconds," and it explained, everything from back when the dinosaurs, but it ended in explaining the universe, the black holes, and things like that. And it totally fascinated me. And also as a kid, I was too young for the moon landings, but when I was a kid, the Challenger missions or the space shuttle missions began. And in this you could see the future. You're launching this airplane full of people and full of stuff, and you just could see how we would colonize space and explore space. That was just so intriguing. Now that didn't happen somehow. I don't know what happened, but we built a space station, of course, but that was kind of it. Yeah. So on that island, I was thinking about what should I do now. I had a little bit lost sense of professional purpose. So I was reading this book, and it was, I hate to admit it, but it was this biography on Elon Musk. And reading that, I can realize that a lot has happened in the space, with the space stuff. When I left thinking about space as a kid or as a kind of a teenager, and it was something that governments did, huge organizations maybe did it, nothing really happened, it felt like, and then I let that interest sleep a little bit, and you became interested, you did your career, you did all these kind of things. But for me, reading this book was like kind of rediscovering space again. I felt like people could actually make a difference, and this guy Musk, he did the difference. He was taking down the cost, he enthusiasted people, and I was starting to think, what could I do? Could I do anything, in space? And because it felt so possible after reading this book. Yeah, I started to think about Beyond Atlas. What could I do? And it felt like, this Elon Musk guy and the other guys as well. Many people were looking at shooting stuff up into space, and they felt like they were getting that part right. So it didn't feel like something for me to try to be the 10th company, launching stuff into space privately. And I also thought that, even if they do it at 10th of the price of what it costs today, it still will become extremely expensive. So my thinking was that if we really truly want to go into space, then we need to make stuff in space for space. So I started to do research on, is there any stuff out there? Is it only the moon and the planets, or is there asteroids? I knew there was an asteroid belt, but is there a kind of asteroids or material close to us? And choking the internet point of this island, it was like, sure, there is loads of stuff out there. So that's kind of how I started thinking about it, not to launch things from Earth into space, but once you are in space, what can you do? How can you travel in space once you are there? And that was kind of the background of the Beyond Atlas. Well, the purpose of Beyond Atlas, it's for me, it's again, what's the purpose of climbing a mountain? That is the same feeling for me. The purpose is the challenge in itself, the challenge of doing what people feel is slightly almost impossible. It's to do something extremely cheap, to go from maybe an Earth orbit and to travel into space, not to look down on Earth, but to travel into space and do something. In my case, I want to first explore asteroids, and then I want to see what kind of resources is on the asteroid. And this feels almost impossible, but then to extract resources from the asteroid to use in space. So basically, the very, very far-fetching purpose of Beyond Atlas is to make it possible, or to help people get the resources necessary to be in space, take the next step, basically. It's a long short story. Beyond Atlas, I was in Marrakesh in Morocco, and we were at this mountain range, the Atlas Mountains, and I was thinking about it. The Atlas Mountains, in the old Roman days, it was considered to be the end of the world. Beyond Atlas, the Atlas Mountains, there was nothing. It was the edge, basically. But it was also the petrified Titan Atlas, carrying the dome of heaven on his shoulders. I mean, that's what the Atlas Mountain, what it was. And I was there with my kids, and we're traversing the mountain range, and I was thinking, you know, that's exactly what we want to do. We want to go into space, not to look down on Earth, but we want to go beyond Earth. We want to go out in space. 95% of all the stuff we do in space is to look down on Earth, but that's not what we want to do. We want to go away from Earth, beyond Atlas, beyond the edge of the world. Well, I mean, lots of people are investing time and resources in this project. People are putting their own free time into the project. I mean, I think that is great. I put my time into the project. That's also a resource. People are supporting the project with giving us discounts on materials or on components, and some people are even giving us components for free in this project. But still, you know, you need money in the project, and I can provide that money. If I don't, I mean, there is not a project. So, and I want it to succeed. That's why I do it. And I wouldn't call it investing, because investing implies that you get something back. And I'm actually not expecting to get any monetary return back. I expect us to solve this challenge. That's what I want to do. I want us to climb this mountain. That's what I want to do. But that's also what I want to get out of it. And that's also what I'm offering everyone else here, is to be part of this challenge. The asteroid we're going to, yeah, we found it. It's a very good story. I found it on the internet. You know, internet's a fantastic place to go if you want to find information. I started out researching. I was like, where to go? And I found out immediately that there is loads of asteroids going around Earth, or near Earth asteroids, but they're not going around Earth. They are kind of passing by Earth, and then a couple of years later they are on the other side of the sun, and they are very, very far away. But in doing this research, I found this asteroid they found it in 2016. And it actually goes around the Earth. So it goes around the Earth at 56 to 85 moon distances from Earth, approximately. And it has done so for 200 years, and will do so for another 400 years. And you know, that's a pretty good candidate, because even though it's a kind of far away-ish, it's kind of always around us. So yeah, that's why. Yeah, when I got back, I was very enthusiastic, and I started calling people. Basically, I started calling people that had stuff to do with the space in Sweden. I didn't know them. Then I kind of explained what I was doing, and many people thought that I was a lunatic, or some people did, but most people actually was kind of excited by the idea. They thought, you know, this is kind of greatish, that because space industry now is, I mean, it's so focused on making profit, and because it's companies doing it, right? So they need to make profit. But here is a project that wants to do something different. I think the project we are doing is actually what people that are interested in space, what they really want to do. I mean, people don't really want to send up a satellite to look down on Earth. They really want to go up in space to explore it. And that's what we are offering. So people got very interested, and they really wanted to see us succeed. So yeah, you know, that's basically, yeah. Or technical challenges. There is many technical challenges. Well, if you start with the most obvious, in order to leave Earth, even if you are up in space, you still need to leave Earth. You need a propulsion system. So you need to propel your spacecraft away from Earth. And you can't use chemical propulsion. You need to use something else. So the first task was to try to find something that is cheap, that is small, and that can take you all the way to this asteroid. Because you need more. It's called delta V. Delta V. It's kind of a measure on how much you must accelerate your spacecraft to get somewhere. And to get to this asteroid, we need more delta V than it takes you to get from the ground up to Earth. You need to pack that in a very small package. So that was the first challenge, and we found a company providing this, and we got into dialogue, and you know, so that's kind of sorted out. But then that electric propulsion was not strong enough for our mission. So in collaboration with this company, we had to make a bigger electric propulsion system. So that they're building now, and that they actually got some ESA funding to do. So yeah, so that is one challenge. And other challenge is to the great distances. I mean, going to space, it's a very, very far. What's the big challenge in that? Yeah, well, it's communication. Because communication, you might not believe it, but the reason why the pictures from distant planets and so on are so bad is not because we are carrying around bad cameras. It's because we don't have the data link to get the data back to Earth. So that's a huge challenge. And there we need a radio, or it's called a transponder, that can work at these great distances and that is small. And that's the company came along and helped us to build that transponder, because you can't buy it actually, unfortunately. So that's a second huge technical challenge. I can go on and go on. Do you need more challenges? Oh yeah, that's the third, right? Yeah, the way you do it, if you navigate, it's you have to position yourself. That is the difficult thing. You have to know where are you. And the normal way of doing it is to use huge antennas back on Earth and use your radio, and then you can do something called ranging, and then you can get your position. You can get your distance and your angle to Earth. Well, okay, you could do that, and you can do it with the transponder that our partners are building. But what happens is that you need this huge dish back on Earth, and that's very expensive to rent. So, well, we'll do that at some points. We need to use this dish, but otherwise we want to do it by triangulation. That means you kind of take the angle to an object, to Mars, for example, and the background stars. You take an angle to Venus, for example, and the background stars, and to Jupiter maybe, and the background stars, or the moon. And then you triangulate your position. And that you can do in the spacecraft using computers, and then get a rough estimate where you are. And that rough estimate is good enough to do the kind of the interplanetary navigation to the asteroid. And it's not something new. I mean, they did it already on the Voyager spacecrafts. It's just that you don't do it if you are in an interplanetary mission, because I mean, if you are NASA, you have these big dishes, and you don't really think about how much does it cost. So, but we have to think that way. So. Yeah, in 2018, in the spring and summer, we paused the project, and the reason for that was two reasons. One was that we had to wait for some of the technologies to get longer in the development. First, it was the electric propulsion unit. We needed to understand how much power that needed, what the mass of it would be, and how much kind of delta V it would give us. So that's one of the reasons. The second reason was that I realized that I would not be able to fund this project myself. Even though people are helping so much, and even we are getting so many things for free and rebated, I still was not able to fund the entire asteroid mission myself. So yeah, so there you have it. Yeah, so then instead what we did, after pausing it and trying to get some external investor on board, but then it was like, yeah, this is not good, we need to work on something. So then we came up with this test mission to test the key technologies in our project in a more controlled environment. So what we want to do is not to divert too much resources from the big project, but use kind of free stuff to launch a small satellite into LEO. And in LEO, we want to test all these really critical things for the asteroid mission. We want to test orbital transfer to get from one place to the other using electric propulsion, and we want to do relative navigation to make sure that once we get to the asteroid, that we can get close to it, and then we want to test the transponder to see that this deep space transponder works properly. And that's three key things we need to check out. Oh yeah, I mean, the mission in itself is cool. The guys asked me, well, you need to write a mission profile on this. You need to write a goal, a kind of a statement. And I said, well, the first priority of this mission is that it needs to be cool in its own right. And they were like, but, you know, that's okay, we understand, but yeah, okay. What's the second goal then? Yeah. So yeah, so what we are going to do is we are going to navigate, launch into one orbit, but then we are going to use the spacecraft to get close to a space debris, to a dead satellite. to make sure that we kind of do this. We need something to relatively navigate to, and we need to change the orbit to something. And then we want to take pictures of it. We want to get very, very close. And this is a huge challenge in itself. I mean, people are investing lots of money to trying to do that. And you also need a lot of delta V to change the orbit as we want to do. And you know, so it's a really cool mission in itself. Okay, electric propulsion, how it works. Yeah, well, I mean, electric propulsion in generally is, I mean, the way that a rocket works is that if this is the rocket, it can only move if you throw something out in that direction. If you throw it out here, then this moves in this direction. That's how it works. And a normal chemical rocket, then you kind of light chemical fuel stuff, and it kind of out there, and the rocket goes that way. The problem with chemical fuel is that the stuff that goes out there only goes out by 300 meters per second or something. I mean, that's how fast it goes. And that gives impulse in that direction. Electric propulsion, there you can get to 6,000 impulse in that direction, which makes that it goes on the same fuel, it goes a lot more in that direction. And so electric propulsion, I can take the method that the one that we are using. There you have extremely thin needles that are porous, and in these needles, indium that you melt is sucked up into the tip of the needle, and the needle is extremely sharp. And when the indium gets up there, it comes up to an electric field, a very, very strong electric field. And what it wants to do is, it wants to leave the needle, and it kind of bounces away in that direction. And it does it then at an impulse, it depends on, but it can be between 2,500 to 6,000 impulse, depending on the electric field. As you can hear, it's like 20 times more efficient than chemical propulsion. So that's kind of how it works. But what makes it really, really cool is, I mean, it's not only 20 times more in that direction, but also the mass of the spacecraft is so important when you try to get up in delta V. And if you look at these big rockets, I mean, what you have to do is you have to bring all this chemical fuel, and when you start the rocket launch, you have to carry all the fuel with you, and then you burn more fuel and you carry less and less fuel. But if you have a higher impulse, then you don't have to carry so much fuel, you don't have to accelerate the fuel. So it's kind of it's not only 20 times more efficient, it's also a lot more efficient since you don't have to carry the fuel. Yeah, so it's a very cool technology, and everyone thinks it's cool, electric propulsion. I think that most people are kind of thinking along these lines when you're going to travel in space. And the follow-up question to electric propulsion is, of course, why don't you do that with rockets based on Earth? Why don't you use electric propulsion to get into space in the first place? And the answer there is actually that you can't get thrust necessary, because if you want to, electric propulsion is good if you are in space, but if you are on the ground, then you need to overcome the G-forces of Earth, and you need to accelerate harder than the G-force of Earth to be able to lift up from the surface, and that you can't get from electric propulsion. You can't get that level of thrust. That's the drawback. You have a low thrust but a very high impulse. Yes, we did win the International CubeSat competition, and that was really cool for us and for the team. It gave us international recognition. And what it was for our test mission that wants to go and visit this space debris. We entered that into the competition, and we won a launch to LEO. It was very, very cool. So the first launch opportunity was the 29th of August this year. So yeah, that's what we are looking into. Yeah, I mean, 29th of August, it feels like it's far away, but in space terms, even for us who are building things fast, it's kind of, you know, tight. But the reason why we will not be able to launch the 29th of August is that we will not be able to get the frequencies in time, because you are going to space, and this is, I mean, I support this, it's the way it has to be. Then you have to coordinate the frequencies, what you're going to use. I mean, you can't communicate with your satellite, and then there is another satellite that can't communicate because you have not coordinated this internationally. And that process takes time, and it's clear to us now, since a couple of weeks back, that we will not be able to get that in time. So then we'll have to launch maybe a couple of months later when we have on another launch. Yeah, the long-term goal of after the asteroid mission, I think we kind of touched upon it. I mean, first I think it's very important to have a goal that is very clear. You know, let's just go to this asteroid and let's put, you know, everything we have into this to make it, you know, to kind of have it well defined. But for me, it's like the first idea I had on this island long ago. It was like, you know, why can't we just make stuff in space to use in space, or, you know, harvest resources in space to use in space, instead of bringing everything up from below? Because again, even if the launch providers, the Musks and other guys, even if they can make it 10 times cheaper to get stuff in space, I mean, just look at the rocket, it will be expensive. You know, no matter what you do, it will be very expensive to get a couple of tons up in space. And if you want to build huge infrastructure in space, you can't just do it. I mean, you can't do it. I mean, so you will have to manufacture things in space for space. Oh yeah, I actually think it could be mined for like basic stuff, for like iron, silicon, zinc. I mean, these kind of nickel, these kind of things probably are in this asteroid, probably. Then I mean, you really would like to find some mineral bound water, not water, but like hydrogen and oxygen bound into minerals. That would be really cool. That's probably not in there because it's a small rock basically. But the reason why you feel that there is, and that's true for all the asteroids, the reason you feel that there is metals in them is that the asteroids, most of them are formed at the same time as the planets are formed. And if you look at Earth, for example, I mean, we have so much metal on Earth, but all the metal and all the heavy atoms, they are gathered in our core, because, you know, the whole of Earth was molten, and then all the heavy stuff, it went down, and all the light stuff, like silicon, for example, so in all the stones, it went up to the surface. And where we have our iron mines today, it's where kind of it has leaked up a little bit of iron from the core. But it's not like that in asteroids. In asteroids, you take everything in the Earth and you shake it and blend it, and then that's what is supposedly in the asteroids, which means that you have a huge, or not a huge, but you have higher concentration probably of minerals in an asteroid than you have in an iron mine, for example, or kind of ish. Yeah. So that's why I believe that there is, you know, mineable stuff on it if you get there. But yeah. Yeah, when the spacecraft gets there, I mean, it will carry a multispectral camera, and what it will do is it will photograph every square meter of this, or even every square decimeter of the surface of the asteroid, and it will gather this spectral information, and that will be a huge amount of data to send back to Earth. So somehow you'll find a way to send as much as you can back to Earth, and then there will be a team of scientists who will try to understand what kind of minerals are on the asteroid, you know, on the surface of the asteroid. So that's one thing, and the other thing is we want to take cool pictures of it. But you know, just to see what it looks like. Is there rocks? Is there sand on it? Is it like a pile of rubble? Or, you know, what does it look like? Yeah, I mean, they need talented people, right? They need, I guess they need people with the imagination, people with vision, people with you know, who wants to put all their efforts in one of these projects. If you look at my project, I mean, we need people who has a kind of hands-on experience, not only theorists, but also people who wants to kind of put things together and make it work. I mean, that's what we need. We need practical as well as theoretical people in our project. If you go into a normal space company, if that's what you mean, they probably need people with a lot of patience as well. I would believe. At least if you hear what people say. I mean, there's lots of, and I can understand why it is like that. I mean, if you send up something in space, it's today it's very, very expensive and costs a lot of money. and you may want to make sure that it's right, and you get all these control routines in place, and you have to be patient with those if you go into a normal space company. Since we are doing our own stuff, we just need to be sure ourselves that it works. We don't need to have those processes in the same way. Yeah, I don't know if that answered the question, but you know, good, great, positive people, I think. Yeah, I mean, I think the immediate thing is just to give, you know, the satisfaction of climbing the mountain. I mean, that's actually what I think they can bring in the near term to us back here on Earth. To engage our minds, to do something we think is great, is fun, something we want to be part of, see that we can achieve something together, all this kind of stuff. I think it can be good for. But in the near term, it will not help us with our challenges back here on Earth. It will not even in the medium term help us. I mean, in the extremely long term, I think it will help humanity to get out in space, for what that is worth. I think also it's a necessity if we want to get out in space to do this, to harvest the resources of space for space. Yeah. Well, sometimes I get the question why I'm so interested in space and to get stuff up in space and to do all this stuff, and I think one of the reasons is that I feel that the world is becoming so small. It's becoming so small. I can sit there and I can look at traveling somewhere. It takes me 24 hours to get to the other side of the globe, and you know, it's not going to get any bigger either. So for me, it's kind of you know, the imagination. I mean, we can't be stuck on this island. Somehow we need to get out there. Maybe not me, or maybe not even my kids, but at some point humanity needs to just expand outside of Earth. It's just, you know, it's kind of a law of nature for me. But then you have these people who are extremely content and want to solve the problems back here, and I respect that. But there is people who look beyond the horizon, and there is people who find, you know, the greatness in what's around them. It feels like, you know, somehow, I mean, it feels like we are standing on this island, and it feels like today we have the paddles and we have the canoes, and we are looking at the horizon on the sea. You can use the paddles and the canoes to go around the lakes and the rivers, but we are standing there, we are trying to use these tools that we have to our disposal to get out there. But, you know, we can't really. We need to make a little bit bigger boats, a little bit better boats. We need to learn how to navigate, how to sail. But then at some point we will learn it, and then I think we'll have you know, the next age of discovery, the next age of expansion, and I think that can only bring positive things to us. Yeah.